suppose omega is open, and f from omega to c is holomorphic, then the image of f acting on omega is open too. Okay, and mappings that have this property that when you take the image of open sets, they form open sets, those things are called open mappings. So in other words, holomorphic mappings are open mappings. So let's put a definition down here. And just generally, in any kind of context, if G goes from X to whatever Y, and G of S is open for any open S contained within omega, then G is an open mapping. So what this theorem is essentially saying is that F is an open mapping. Okay, proof. All right, so let's draw a picture. We have the image here of F of omega, and the claim that it's open is the claim that whatever point we take inside, we have some little ball around that inside the actual image, right? So let's pick some arbitrary point W. So pick W belonging to omega. We're going to show that there exists a ball around W that's fully inside the image of F acting on omega. Okay, so since F belongs to the image like this, so since it is inside the image, actually let's call it W0. Need W later. Then some point maps onto it, perhaps many points, but at least one point maps onto it, and pick Z0 such that doesn't matter which one you pick, but just pick one. And there might just be one, but who knows? Okay, so we can pick something like this. So consider this map. Capital F of Z, which will be equal to F of Z minus W0. This is a nicely holomorphic mapping, right? And has a 0 at Z0. Yeah? So Z0 is somewhere inside the domain. So let's put the domain over here. So this here is Z0, and we're mapping from omega into F of omega like this. Yeah? So capital F has a Z0, sorry, capital F has a 0 at Z0. Yeah? Yeah? But the 0 has to be isolated because it's a holomorphic mapping, right? So it's an isolated 0. So therefore there exists some radius r such that on the boundary of a ball of radius r, there are no other zeros of capital F. Yeah? Because it's isolated. Yeah? So is the empty set. Okay, and that means that if we look at little f, no, let's not say it that way. That means if we take the absolute value of this guy, capital F, then the absolute value has to be strictly bigger than 0 on the boundary, the empty set, on the boundary of the ball. Because if that wasn't true by compactness, we could find a point such that it actually was a 0. Right? So thus is bigger than delta for all z belongs to the boundary of the ball of radius r around z0 for some delta. Doesn't matter how small it is. Right, so what have we got? We've got some little radius r around z0. And the image of this guy cannot get too close to omega 0. It has to be at least delta away from omega 0, right? Because that's exactly what this thing says. You with me? Give me a thumbs up. Okay, good. So we don't know much about the image of the boundary of this ball. We do know it stays away from W0 by at least delta. So let's suppose it wraps around twice, whatever. Yeah? Maybe it wraps around once, maybe it wraps around 57 times. But we do know that the image is at least delta away from this thing. So bigger than delta. Yeah? Okay, so with this picture in mind, the natural thing to do is to argue that if we put a ball of radius, say delta over 2, around W0, then everything inside that ball will actually be inside the image of f of omega. That's what we'd expect somehow, right? That'd be the natural thing to expect from this picture. Yeah? And that's what we're going to try and argue. So we're going to try and show that if we put a ball of radius delta over 2 around W0, it'll actually be inside the entire image of f acting on omega. Okay, so let's put that as a claim. Or let's say what we're going to do. We will show okay, and if we do that, then we're done, because that means that we have some ball which is completely contained within omega around our arbitrary point W0. Yeah? So let me see if I can erase just half of the board. It's probably not going to work. Okay, I'm going to erase the entire board, and we'll just start from this point. Okay, let's pick up where we're going. So, where we left off. So this is our picture. So I'm going to make a small picture and then a bigger picture. So this is omega. This is, say, Z0. This is the image. This is W0. And we found some radius r like this. Okay, where the image of this thing was, say, wrapping around 2 times like this. And it was always at least delta away. Okay, and this is radius r over here. Cool. All right, so this is where we were. Yeah, and we will show, so our claim was the following. Or I said we will show, but okay, claim that the ball of radius delta over 2 of W0 is actually contained within the entire thing. And that's what we need to show to complete the proof. Okay, cool. All right, so proof of claim. Pick some arbitrary W inside this ball of radius delta over 2 around W0. Okay, and consider the mapping f of z minus W. Okay, and we're going to break this up into f of z minus W0 plus W0 minus W. Okay, and then look at these things separately like this. So this f of z minus W0, previously we called this capital F. So let's write this as capital F of z, and let's write this thing, which is just a constant function, right, having picked the W0, let's write this as g of z. Is just this constant function W0 minus W, which is a nice holomorphic function. Yeah? And recall f of z was little f of z. Yeah? That's how we define f, which is also a holomorphic function. And note, that the capital F of this thing, for any z around the boundary of the ball of radius r around z0, is bigger than delta for any z. This is how we found this delta, right? And by construction, since W0 is inside the ball of radius delta over 2 around W0, this guy is just equal to delta over 2 for every single z, right? Every single z no matter where, because it's just a constant function, but let's just write it like this. Okay, let's just write it like this. So, capital F of z, absolute value, is bigger than capital G of z for all z belonging to the boundary of this thing. Yeah? Cool. So you can see where this is going, right? So, by Roche. The winding number, not the winding number, the number of zeros of capital F inside the ball of radius r around z0 is the same as the number of zeros of capital F plus G, right? It's exactly the same as Roche's theorem. And capital F plus G is exactly this function, f of z minus w. Let's put the z's in because it looks strange without the z. Yeah? Inside. And there is at least one zero of capital F inside this ball of radius r around z0 because that's how we set it up. Is zero, right? That's how we set things up, yeah? So definition, yeah? So there is at least one zero of capital F plus capital G, i.e. of this thing. Yeah? I.e. there exists R inside this ball. There exists Z inside this ball of radius R around Z0 such that capital F of Z is equal to W. And that's it. Yeah? So we've shown that if we take, let's blow up this picture here. So I'm going to blow this up over here. If we have a ball of radius delta over 2 around this point W0, so this is W0 here, and this is the radius delta over 2, then every single w inside here, so we pick some w right at the start of the argument, just picked one, right? Then there exists some guy, so now we're going to blow up over here, so this is z0, and this is the ball of radius r. There has to exist some z, which is mapping onto this guy right here. Let's put the z with leading nearest. Made a mess. There's some z which maps onto it, right? That's exactly the statement of what we've just shown, yeah? And therefore, this entire solid ball of radius delta over 2 is contained within the image, yeah? And which proves the claim. So, which proves the claim. Okay, so this is this proof is kind of clever, and let's make some remarks. So, firstly, if we had this situation where z0 happened to be a point where the derivative was non-zero, then this is kind of trivial, because if the derivative is non-zero, then locally the function is well approximated by this affine mapping, right? So it's no surprise that if we take a very small ball, it's going to actually cover the point w0 with some kind of shape, right? And in fact, since we're doing holomorphic mappings, and the derivative will be just this mapping which dilates and translates space. If we take the image of a small ball on a small scale, it's another small ball, right? And it will definitely contain w0. So if this was a function that was differentiable at z0, this is not hard to prove. This is kind of not surprising. Do you see what I mean? Yeah? If it was differentiable with non-zero derivative. Yeah? I mean, you all did multivariable calculus, right? So you learned about the inverse function theorem, right? That if you have a point where the function has derivative or determinant of its derivative non-zero, then it's locally invertible around this point. Yeah? Yeah. And you needed specifically that the derivative or the determinant was non-zero, which implies the derivative is non-zero, so that the image of a small ball was actually something that contained your image point, and you could reverse back from it. All right? So if you look back at the proof of that, you'll see that inside the proof of that is the claim that we can contain any small ball around the image with something. And it's just not hard, it's just using differentiability. Yeah? Does that make sense to you? Yeah, give me a thumbs up if that seems some sort of meaningful. Okay, cool. The difficulty arises if we don't have a non-zero derivative at z0. Yeah? But if we don't have a non-zero derivative at z0, then what kind of thing do we have? Well, most likely we have something which is like this, where we have the function capital F equals f of z minus w0 has a zero here, and if it has a non-zero derivative, then the order of the zero will be bigger than 1, right? So this will be like z minus z0 to some number m times g of z, right? If the first derivative of this guy was non-zero at z0, yeah, where m is bigger than or equal to 2. Yeah? Because then if we differentiate this, then the derivative will also be 0 at z0. Yeah? And in this case, well, we have very well-behaved function. We have a very well well understandable function, because what is this doing on a small scale? It is just taking this ball, and this thing is more and more just like a constant as we approach z0. So it's taking this ball and it's wrapping it around. It's wrapping it around m times, and then it's sticking it back here. Let me say that better. So this thing by itself is just taking this ball and wrapping it around m times, but the actual function f is taking this ball, wrapping it around itself m times, and then sticking it over here. So it'd still expect that the image would contain a small ball over here. Yeah? So if you wanted to, you could just use this fact and work more carefully with your hands. When I say work with your hands, it means do elementary arguments, don't use powerful theorems, and show that no matter what m is, then the image of a small ball around z0, the image of a small ball around z0 will contain a small ball around w0. Because look, if we just consider this mapping, so consider f of z equals z to the m, yeah? Then what is it? So 0 is sent to 0 in this mapping, but if we consider a small ball of radius r around 0, this is mapped to a small ball of radius r to the m, yeah? Yeah? And that's the worst thing that this thing can do in terms of compressing space, right? Yeah? Yeah? So if I just ask you to prove this theorem for this mapping, then where the derivative is non-zero, which is anywhere away from 0, then it's fine, it's easy to do, because what I just argued, that it's locally approximated by its first tangent. But at zero itself, we can still do it, because the structure of the way this thing is collapsing space is incredibly regulated. It's collapsing space in a very orderly way. Is that making sense? Yeah? And this is we have such powerful theorems about the way these functions behave at any arbitrary 0. If it's collapsing space, it's also collapsing space in a way which is basically analogous to this. Yeah? So it can't do anything weird. It can't take the image of a ball and just like squash it down to nothing. Yeah? The worst it can do is take the image of a ball and wrap it around itself lots of times and make it smaller that way. But it can't just evaporate space, right? Which an arbitrary mapping from Rm to Rm can easily do. It's trivial to come up with examples, but these guys can't. Yeah? So this is a slick proof using the fact that we have Roche's theorem, and it's this tool we have, so we use it. And it might seem a little bit unnatural because it almost seems like it's overkill, because this function g we define is just a constant function, and we have this trivial equality. So it seems odd to use Roche's theorem here in a way, but if you think about what Roche's theorem does, then it's just about the fact that capital F plus G is forced to wrap around the same number of times as capital F, and it's really not that far away from these kind of ideas. So if you want to do an elementary proof like this, using this fact, that the worst that can happen is when you have something like this at 0, you'd be arguing in a way which is somewhat following this. So this is the modern way to, like, this is what happens to proof. So as time evolves, people find slicker and slicker ways to go straight to the point. But the heart of the issue here is exactly these things, and particularly this example. It's about the way that holomorphic mappings can squash down space, and they can't squash it down in any particularly strange way. They squash it down in a very regulated way.